At the beginning of 2025, Jensen Huang, the CEO of the company that makes the chips powering almost every major AI system on the planet, stood in front of an audience and said quantum computing was at least 20 years away from practical application. By the end of that same year, he was publicly walking that statement back. And by October 2025, NVIDIA had announced something called NVQLink, a piece of hardware infrastructure he described as the Rosetta Stone connecting quantum and classical supercomputers. In a matter of months, the man who built his company's entire identity around GPU dominance in AI had pivoted to saying that in the near future, every NVIDIA GPU scientific supercomputer will be hybrid, tightly coupled with quantum processors to expand what is possible with computing. That pivot is not just a story about one CEO changing his mind. It is a story about a shift in the physics of what is possible with AI that is happening right now, faster than almost anyone in the mainstream technology press is tracking. Stick around, because by the end of this video, you are going to understand exactly what a quantum AI hybrid chip actually is, what problem it solves that classical AI silicon cannot, and why the architecture that is emerging in 2026 looks nothing like the future the AI industry was planning for just 18 months ago. To understand why hybrid chips matter, you first need to understand the specific wall that classical AI is running into. Because this is not about raw computing speed. Modern GPUs are extraordinarily fast at what they do. The problem is the category of what they do. Every major AI system you've used, every large language model, every image generator, every recommendation algorithm runs on a fundamentally classical computing architecture. Billions of transistors switching between ones and zeros, arranged in parallel so that millions of multiplications can happen simultaneously. That approach works brilliantly for the kind of mathematics AI depends on most: matrix multiplication at enormous scale across enormous datasets. GPUs are essentially purpose-built matrix multiplication engines, and for that job, they are close to optimal. But there is a category of problems that sits at the heart of some of AI's most important frontiers, problems that classical matrix multiplication handles with increasing inefficiency the more complex they get. Global optimization across thousands of variables simultaneously, sampling from high-dimensional probability distributions, simulating the quantum behavior of molecules for drug discovery or material science, the combinatorial search problems that arise when you try to plan routes, allocate resources, or find the best possible configuration across a system with billions of interacting components. For these problems, classical computers don't just slow down, they hit walls. The number of operations required to find the best answer scales so fast with the size of the problem that, at a certain point, even adding more GPUs doesn't meaningfully help. You're not limited by how fast your hardware is. You're limited by the mathematical structure of the problem itself. Smash that like button right now, because what a quantum processor does to those problems is not just faster, it is categorically different. A quantum processor, or QPU, doesn't manipulate bits that are either 0 or 1. It manipulates qubits, which can exist in combinations of 0 and 1 simultaneously through a property called superposition. When you combine superposition with entanglement, the phenomenon where two qubits can be linked so that the state of one instantly influences the other, you get a processor that can evaluate a vast number of possible solutions to a problem at the same time, rather than checking them sequentially. Think about the optimization problem this way. Imagine you are trying to find the lowest point in a landscape with 10,000 valleys. A classical computer has to check valley after valley, keeping track of the lowest one found so far. A quantum processor uses interference, the same phenomenon that makes waves cancel each other out or reinforce each other, to amplify the probability of landing on the globally optimal valley, while suppressing the probability of getting stuck in a locally good but globally mediocre one. For problems of sufficient complexity, that is not a speed advantage. It is a completely different mode of solving the problem. Google demonstrated what this difference looks like in practice in October 2025. Using just 65 qubits, its Quantum Echoes algorithm ran 13,000 times faster than the Frontier supercomputer, the most powerful classical machine that has ever been built on a specific class of physics simulation. Not somewhat faster, not 10 times faster, 13,000 times, on 65 qubits against the pinnacle of classical supercomputing engineering. Subscribe right now, because that number only makes sense if you understand the catch. And the catch is what makes the hybrid architecture story so genuinely interesting. A quantum processor running in isolation is not a replacement for classical AI hardware. It is not even close to one. And every serious person in the quantum computing field says this explicitly and emphatically. The reason comes down to what qubits are good at versus what they are terrible at. The matrix multiplication that forms the backbone of training and running large language models maps efficiently and naturally onto classical GPU hardware. Trying to run standard AI inference on a quantum processor today would be like trying to use a scalpel to pave a driveway. Technically a tool, completely the wrong one. Qubits also have a fundamental fragility problem. They decohere, meaning they lose their quantum state and start behaving like ordinary classical bits due to temperature fluctuations, electromagnetic interference, and even cosmic rays passing through the building. Every quantum computation requires a constant, real-time classical computing layer running alongside it, detecting errors, correcting them, and keeping the quantum state coherent long enough for the computation to complete. That classical error correction layer has to operate fast, not milliseconds fast, microseconds fast. If it lags, the quantum state collapses before the answer is ready, and the whole computation is lost. This is precisely the engineering problem that NVQLink was built to solve, and understanding what it actually is changes how you interpret the entire hybrid chip story. NVQLink is a hardware interconnect architecture announced by NVIDIA in October 2025. Think of it as a specialized ultra-high-speed communication bridge between a quantum processor and a GPU cluster, engineered specifically to meet the timing demands of real-time quantum error correction. The key technical specification is latency. The NVQLink architecture achieves a transport latency under 4 microseconds between a quantum processor's control system and in an NVIDIA GPU performing the error correction calculations. For context, 4 microseconds is roughly the time it takes light to travel about a kilometer, and that speed is not a luxury. It is a hard engineering requirement. Qubits in current systems have coherence times measured in microseconds to milliseconds. If your error correction loop takes longer than the qubit can hold its state, the computation fails. NVQLink's sub-4 microsecond latency is designed to be inside that window, giving the GPU enough time to detect and correct errors before decoherence destroys the result. When Quantinuum connected its Helios quantum processor to NVIDIA GPUs through NVQLink, the team demonstrated real-time decoding of quantum error correction codes at a reaction time of 67 microseconds, which exceeded the system's 2 millisecond requirement by 32 times. That is not a marginal improvement. It means the architecture has significant headroom to scale to larger, more complex quantum systems without hitting the timing wall. CTTRL, which makes quantum control software, reported a 50 times reduction in classical overhead and a 5 times speed up in overall computation time by integrating NVQLink into its stack. Don't forget to subscribe, because the software layer on top of all this hardware is what makes the whole system usable for AI developers without a PhD in quantum physics. NVIDIA's Q2Q platform is the software bridge that completes the hybrid architecture picture. If NVQLink is the physical highway connecting a quantum processor to a GPU cluster, Q2Q is the navigation system that decides which workloads travel which direction. The platform became publicly available through its CUDAC real-time API in March 2026 at GTC, and it allows developers to write code that treats GPUs and QPUs as components of a single unified system rather than 2 separate machines that happen to sit near each other. An engineer building a quantum AI hybrid application doesn't need to separately orchestrate the classical and quantum portions of a workflow and manually manage the data transfer between them. Q2Q handles the workload routing, the error correction orchestration, and the real-time feedback loops automatically within the same programming environment that developers already use for standard GPU accelerated computing. That matters enormously for adoption. The entire history of GPU computing in AI is a story of abstraction. CUDA, NVIDIA's original programming framework for GPU computing, is the reason GPU accelerated AI went from a research curiosity to the foundation of a multi-trillion-dollar industry. It made GPU programming accessible to software engineers who weren't hardware specialists. Q2Q is attempting to do the same thing for quantum GPU hybrid computing, and it is doing so with the same strategy. Build the abstraction layer so deep and so complete that developers don't need to understand the underlying physics to use the capability. Let's talk about what hybrid actually looks like in practice, because the architecture is beginning to appear in real data centers right now, not just in research papers. In February 2026, a company called SDT opened what it described as Korea's first commercial quantum AI hybrid data center in Seoul's Gangnam district. The facility connects an Anion computing quantum processor to NVIDIA DGX B200 GPU clusters through NVQLink. The workflow architecture is exactly the division of labor the hybrid model was designed around. NVIDIA GPU systems handle data encoding, variational optimization, control loops, and results post-processing, which are computationally intensive but classically tractable tasks. Latency-sensitive quantum kernels, the specific operations where superposition and entanglement provide an advantage, are dispatched to the QPU. The result is routed back to the GPU for post-processing, and the classical remainder of the workflow continues. The quantum processor never does more than it's actually better at. The GPU never wastes cycles on problems that QPU handles more efficiently. At a national laboratory level, Lawrence Berkeley. National Laboratory used NVQLink to integrate the open-source QBC quantum control system with NVIDIA DGX Spark hardware, and is now running AI-enhanced quantum control experiments, including using AI models to improve readout classification and gate tuning on the quantum hardware itself. That last detail is particularly significant because it shows the relationship running in both directions. Not just AI accelerated by quantum, but quantum hardware calibrated and maintained by AI. The two technologies are now actively cooperating to make each other work better. This is what the industry means when it talks about convergence. It is not a metaphor. It is a physical architecture where a GPU is running AI models to calibrate a quantum processor, and that quantum processor is simultaneously solving optimization problems that the GPU cluster cannot efficiently address on its own. Now for the honest assessment that most coverage of this topic skips entirely. Is this the end of classical AI? The answer is no, not remotely, not in any near-term time frame, and the people actually building this technology are the first to say so. Classical deep learning has not hit a ceiling. GPUs continue to improve. NVIDIA's own Vera Rubin platform, announced in early 2026, delivers 10 times the inference performance per watt of its predecessor. The problems that GPUs solve better than any quantum system, which is most of the problems involved in training and running large AI models, are not going away. The matrix multiplication, the attention mechanism calculations, the gradient updates that train a neural network. None of those benefit from quantum approaches today or in the near future. What hybrid chips represent is not replacement, it is extension. The AI pipelines that are going to look meaningfully different in a hybrid world are not the ones running standard language model inference. They are the ones that hit the specific categories of intractability that classical hardware cannot brute force past. Drug discovery pipelines that need to simulate molecular quantum behavior. Financial optimization systems that need to search across millions of constraint combinations simultaneously. Materials science research that needs to explore the quantum behavior of new compounds. Logistics and supply chain planning at scales where classical optimization algorithms take days or weeks to converge. In all of those domains, a QPU is not replacing the GPU. It is taking the bottleneck subproblem, the piece that was forcing the classical system to either approximate or wait, and handling it in a fraction of the time. The GPU gets the result back and continues. The overall pipeline speeds up without the classical architecture changing. The bigger picture of where this is all heading became clearer when NVIDIA disclosed that more than a dozen supercomputing centers and national research institutions across Asia and Europe joined U.S. facilities in adopting NVQLink. Brookhaven, Fermilab, Lawrence Berkeley, Los Alamos, MIT Lincoln Laboratory, Oak Ridge, Pacific Northwest, and Sandia National Laboratories are all integrating quantum processors with GPU clusters through the same interconnect architecture. Japan's National Quantum AI Research Center, Singapore's National Quantum Computing Hub, and Australia's PAWSI Supercomputing Research Center are doing the same. When the institutions that define the frontier of scientific computing all converge on the same architectural approach simultaneously, that is not a prediction about the future. It is a description of the present. The quantum GPU hybrid architecture is not being planned, it is being installed. The Quantum Insider's consensus forecast from its panel of experts heading into 2026 put it plainly. If 2025 was the year hybrid approaches became interesting, 2026 will be the year they become the default. The major cloud providers, national laboratories, and hardware companies have converged on the same conclusion. The next decade belongs to heterogeneous compute, meaning CPUs, GPUs, and QPUs working together, each one handling the class of problem it is physically best suited for, inside a unified system that routes workloads automatically between them. Here's the clean synthesis of everything we've covered, because this story deserves a precise landing. Classical AI is not ending. What is ending is the assumption that GPUs alone are sufficient for every category of problem that AI will need to solve in the coming decade. The frontier is moving into territory where some of the most important problems, drug discovery, materials science, optimization at scale, require capabilities that classical silicon cannot provide without sacrificing either accuracy or time. Quantum processors, tightly coupled to GPU clusters through low-latency interconnects like NVQLink and orchestrated through unified software platforms like CUDA-Q, provide those capabilities without requiring the classical architecture to be replaced. Jensen Huang changed his mind about quantum, not because the technology suddenly became more impressive. He changed it because NVIDIA figured out how to make quantum a component of the same system its customers already depend on. That is a fundamentally different proposition than asking the market to adopt quantum as a standalone replacement. And it is the architectural insight that makes the hybrid era Not a future prediction, but the thing that is already being built right now in laboratories and data centers around the world. Quantum machine learning alone is projected to contribute $150 billion to the broader quantum computing market as these hybrid systems mature. That number doesn't come from quantum processors replacing GPUs. It comes from hybrid architectures, unlocking categories of AI capability that pure classical systems simply cannot reach. The chips being installed in supercomputing centers today are not the final form of this architecture. Error correction is still maturing, qubit counts are still limited, and the software ecosystem around hybrid programming is still in its early days, but the direction is set. And for the first time in the history of computing, the most important question inside a data center isn't just how many GPUs are in the rack, it's whether there's a QPU alongside them. Let us know in the comments. Which application of quantum AI hybrid computing do you think will arrive in the real world first? Drug discovery, material science, or something nobody is talking about yet? We rate every single one, and we'll see you in the next video.